Hello, welcome back to another lecture in this series on low-level boot sector programming, operating systems, development stuff. Today I'm going to be talking about carrying on from the memory stuff that we looked at last time. So last time we looked at how we could write directly to memory and store data in there. So memory is basically a long sequence of bytes that we can access using an address, just like an index. So we can say I want the byte at index 0, I want the byte at index 1, etc. But we're going to look at the stack today. So sometimes it's inconvenient to always access memory using a direct address. Sometimes you don't care about where you store the data, you just want to store it and then retrieve it later on. So that's when the stack comes in. And then just at the end of the lecture I'm going to talk about control flow. So looking at how we can implement some logic, some kind of, like if, else, that kind of thing, branching in assembly, which is it's not too difficult really, but it takes a little bit more thought once you've been used to doing it in a high level language like C or Python or Java or something like that. So okay, so we'll start off. I'm just going to work through examples again. I'll just play around with some code and we'll see what happens really. Like I said before, it's always difficult just writing in assembly, so probably I'll make some mistakes and hopefully we'll figure out how to fix them, and that's a good way of learning. Okay, right, let's have a look then. So I'm going to start to play with the stack. So open my boot sector. So here's my boot sector. This should start to look more familiar now. So I've got my org statement here that helps the assembler to calculate the offsets from my labels in memory. This tells this 7C00 is the place that I get loaded into BIOS. I've got this diagram again here. So this is where we're getting loaded in memory. So my boot sector is here. And then I've got this code here, which is I use the interrupt 10 hexadecimal, so that's 16 in decimal. So I want to use BIOS scrolling teletype, so I use OE. I put that in the high 8 bits of the X register, and I put the character I want to print into AL. And now that we can print a character to the screen, we can get some feedback on what's happening in our code, and we'll find this is very useful when we come to play around with the stack and also looking at the flow control stuff later. So this should just print an X. So this is stuff we've done before. So I'm running my emulated PC and it's booted up my boot sector from the disk and it's printed an X. Okay. Now one thing we looked at in the last lecture was that we could so rather than me printing directly from a register like that, what I could do is store my character in memory somewhere. Let's put it at 0x, it doesn't really matter, but let's put it up here because I think it's not going to stomp on BIOS. I'm going to load a character, so I'm going to type byte because I just want to store a single byte at that address. Otherwise the assembler doesn't know whether I want to store 8 bits, a single byte, or 16 bits, 2 bytes. So I tell it. And I'm going to store character, let's put an A in there. Let's just check that runs, okay. Just check my code. Okay, it's printing a U now just because I didn't put any. I've not put anything in AL for BIOS to print, so it's just printing a random character. So now what I'm going to do is move. Let's just assume that I stored this A in that address at some point somewhere else in my code, and now I want to print it out. So now I have to move it back into my AL register, which is where BIOS looks for printing a character when I call the teletype in routine with the interrupt. And I'm going to say move into AL the byte that's stored at this address and print that out. And there's my A, okay. So now what I'm doing is I'm just storing that A somewhere in memory, so here at 900, which is, if I look on this diagram, it's going to be somewhere up here in this free data block. So I'm using memory to store it, but supposing that I don't want to care about where it gets stored in memory, I just want to maybe use memory for some temporary storage that I'm going to do some things with, and then later on I don't care about it. Now we looked at registers like AX, BX, CX, DX, general purpose registers, which when we're doing computations, we can store 16-bit values in those, and those are in the CPU core, and it's very fast for the CPU to access those and to modify them and to use them in calculations. But the problem is we've only got a limited set of registers. So when we want to store more data, if we're doing some computation where we've got a lot of stuff to store, and then we're doing calculations, and then we take some of that data and change it and store it, and then the next time around the loop we maybe get some more of that data and store it, we'll find that we can't store everything in the registers that we need to. So we need to use memory, which is why our computers have so much memory, because we need to use it. But because I've got a limited number of registers, I want some other way to store it. Now I've got all of memory that I can store data in, like I'm doing at the moment. I could use up as far as I could reach with my addressing. I could store all my bytes in there, but it's just inconvenient really, because if I'm only storing things temporarily, then I don't really want to be remembering where everything's stored. I might, if I store something in an absolute address in memory and I want to use it later, I can use it, but then if I forget where I stored it and I store something else over the top of it, it means that I've then got to think about how do I manage the memory. And this is something that when you come to writing operating systems, you have to have a whole like section of the operating system code is there to deal with memory management, to make sure that memory is used and freed and allocated efficiently. And it's not a simple thing to do. But anyway, conveniently, most CPUs have this idea of a stack. And a stack is just very simply, the stack is set up somewhere in memory, and we push values onto it, we push data onto it, and we pop data off it. So we push values onto the top of the stack, and as we keep pushing data onto the stack, it grows, and then we pop values off the stack when we want to use them, and it shrinks again. And it means that once we pop values off the stack, that address that thing was in can be used again. And because we just use push and pop to access it, then we don't need to worry about those issues to do with stomping over memory that we might need later on and stuff like that. So let's play with the stack. So what I'm going to do is, there's two functions that we need. So there's push, and if I say push A, and then if I do this pop AL, then we should find, what did I do wrong there? So I push okay, so this is an important thing. Like I said, it's good to make mistakes. So the problem here is that I've pushed, when I said push A on to the stack, an important thing with the way a stack works is that it deals with 16-bit chunks. So when I push a value onto the stack, whether I push a single character on or a word, 2 characters, 2 bytes, then it always allocates 16 bits for that particular element of the stack. So the stack you can think of working in 16-bit units. So when I pushed that A on there, when I tried to pop it off into AL, which was the lower 8 bits of the AX register, then it told me I couldn't do that. So let's try again. So let's just try this. If I pop it into the X, let's see if this works and what happens. Okay, so we're printing a character now, but it's not the one that we wanted. So what I'm going to do now is I'm going to move the lower byte from BX which I just popped off the stack into AL, and it should print my A. There's my A. Okay, that's good. So if we go back, so what's happening here? Well, if I push a few more things on, it'll be clearer, but when I say push A, it's storing this somewhere in memory on the stack, and when I say pop BX, it's taking the last thing that I stored on the stack and it's storing it into the BX register. The reason I popped it into BX was because, well, firstly I've already set up the high bit of the AX register with this BIOS teletyping value OE, and I didn't want to overwrite that when I popped off the stack. So I've just stored that that A that I pushed onto the stack into the BX register now. And now, because I want to print it using the teletype BIOS routine, I need to put that character into the lower bit of the AX register, so AL. So I use this here to do that, and it prints it out. So let's just try something else. Well, if I do this, if I do push A, B, and C onto the stack, what's going to print now? Okay, last time it printed an A. Okay, now it's printed a C. Because I pushed A, then I pushed B, and then I pushed C onto the stack. And when I did a pop into the BX register, it's going to pop the C character off there. Actually, what it's popping off there is the 16-bit value, which will be the low rate bits will be C. And when I push a single byte onto the stack, it would have put the higher byte as 0, so it would have automatically made that single byte character into a 16-bit value with 0 as the high byte. So that's what the stack does. So let's just have a look then if we put some more of these in. So this pop BX, let's just repeat this. So now what I did, I pushed ABC onto the stack, and now I'm popping off 3 times from the stack. So let's see what happens. Okay, so there we see I've printed CBA. So it's printed them in reverse because I pushed them on A, B, C, and then I popped them off. C comes off, then B comes off, then A comes off. So I'm using the stack now to store stuff in memory. And like I said, I'm not worrying about where they're stored in memory. I'm just pushing them on there, and when I need them later, I'll pop them off. It also means that once I've popped them off the stack, I don't need later when I push something else on the stack, it's going to use that memory of the last thing that was popped off the stack. So I don't need to worry about that. So the stack is very convenient, and we'll see later on that it's convenient for implementing functions and abstraction of functions, which higher level languages do, for especially for passing parameters in functions. Because the function is temporary, so when the function finishes, those local variables and those parameters later on can be freed up. So, well, let's just try something. So I pushed 3 things onto the stack, and I popped 3 things off. But what will happen if I pop another thing off the stack? Okay, so now I've got, so it's C, B, A, and then some random byte. Let's just run that again and see if we get the same byte. We might do. Oh yeah, we always get the same one, but that's not guaranteed. But all that's meaning is that I've sort of, by popping off more things than I put onto the stack, I've sort of gone outside of the stack. Okay, so I'm basically gone into random memory. Okay, so you basically when you push stuff off the stack, you should pop them all off again when you're using them, and not go beyond the end of the stack. So that's how the stack works. Now, as I said, when you push things onto the stack it grows in size, and when you pop them it shrinks in size. But we're going to see that it can be a bit confusing, because the way, at least by default on x86 machines, the way the stack grows is downwards in memory. So the actual base of the stack is at a high value in memory, and as we push things onto the stack they actually go into lower addresses, and when we pop them off the stack shrinks back upwards again into memory. The reason it does that is because, well, usually because when you have an application, sometimes you want to use a stack usually for temporary variables, and you want to use what's usually called a heap, or just other memory, to store more permanent things. And because you don't want them to overwrite each other, you usually start the stack at the top of memory and start the heap at the bottom of memory, and the stack grows down and the heap grows upwards, and then it means that they should stay out of each other's way until you use all of the memory up. So that's why it grows downwards. But we can show that. Let's just have a play and we can demonstrate what's happening there. So we push those things onto the stack. Well, the first thing we need to just think about is where is the stack, and how does the CPU know where to store things on the stack? Well, like I said last time, some of the registers in the CPU are special purpose registers, and there's two registers that the CPU uses for tracking the stack. One of them points to the base of the stack, the bottom of the stack, and the other one points to the top of the stack where you push things onto it. And when you create your in your code, you can set the stack to wherever you like, and by setting one of these pointers, the base pointer, and when you push things onto the stack they'll then be pushed on top of that pointer. So I'm going to just set those. So the two pointers are SP and SB. So I always think, I forget exactly what they mean, but stack pointer I usually think of just the pointer to the top of the stack, and SB I think of stack base, so that's the bottom of the stack. Now the thing is, we don't know we could probably find out later on if we wanted to, but we don't know where the stack is set at the moment. We don't know where BIOS set the stack when it loaded us. So it's usually a good idea, once you've started your boot sector, to set the stack somewhere where you know it's safe, that it's not going to overwrite anything else. So I'm going to set the stack base now, and then I'm also going to use that to look more closely at how the stack is used, to show that it grows downwards, and also to look at where also to show that when I push on a character it actually uses 16 bits, 2 characters worth of data on each stack element. So I'm going to do that. So first of all, if I run my, let's just put my code back, so let's put some comments in my code. So let's just say push characters, and then here is pop and print, and we do that 3 times. Okay, so we'll just check my code again that it's working. Yes, there it is. So it's printing the characters in reverse off the stack in the reverse order that I push them on. And now what I'm going to do is just set the stack somewhere else. Now if I look at my memory, I'm going to set it to, I know this area is free because BIOS leaves this free for our code to use. So I'm going to set the stack base pointer somewhere up here at probably 0x8000 hexadecimal, and that means that when I push things onto the stack it's going to grow downwards. But if I set it up there somewhere, then it should mean that it won't overwrite my code. If I wanted to play around with this, and feel free to do this with your own code, try putting the stack like around very close to your boot sector code and pushing things onto it, and eventually you'll corrupt your own code and you'll lose control. So you see, it's important. Like I said in the last time, we've got full control over the computer now, so we've got to be careful what we're doing, and we've got to be aware of how to use memory. There's no operating system helping us, so we're doing all of that management. So let's set my stack up. So to set the stack, the new location of the stack, I'm going to set the base pointer So I'm going to say move into the stack base OX 8000. Okay, that's good. But the other thing I also have to do, I've set the base of the stack now, but I need to set the top of the stack. So I'll move stack pointer, and I'm going to set that to the stack base, which means I've set the top of the stack to the bottom of the stack, which just means there's nothing in it yet. And when I push something onto the stack pointer will grow by 16 bits, but it will grow downwards. So let's just check my program still works. There we go, let's just check that. Yeah, there we go. Okay, like I said, it's easy to forget the names of the registers and things, especially if you're not doing assembly all the time. So the registers that I should have used are BP for the base pointer and SP for the stack pointer, the pointer to the top of the stack. So there we go. I told you I'd make mistakes. Yeah, this is why we write in higher level languages usually. It is very difficult to just pick up a piece of some assembly work and start writing code in assembly. But the good thing is that in assembly there are only a very few of all the instructions that are available on the CPUs. There are only very few that are used commonly. If you disassemble any code, you'll see that you'll see add, subtract, multiply, move, on the common registers, jumps, and you often see some of the other less used ones in there. So anyway, let's carry on after that little hiccup. So I've set up my stack now. So I've set the base pointer to 8000 hexadecimal, and I've set the stack pointer to it, and I'll see when I run the code it does exactly the same as it did before, only now I know where the stack is because I've set it up, which is good. So let's go back. Right, so what I want to do now is I've pushed these things onto the stack here, and I'm going to I'll put a jump here because I'm going to ignore that rest of the code for now. I don't want the CPU to execute this remaining code, so I've put this jump on here. Okay, so I'm not printing anything at the moment. Now I want to show how the stack grows. So I set up the base pointer to address 8000, and I pushed an A on, then I pushed a B on, then I pushed a C on. So let me just see what happens if I print the character at address 8000. Let's see what happens here. Okay, it doesn't print anything. So what does that mean? Well, it actually means that the 8000, if it stored a byte in there, that will be above the stack. The first thing that I push on, the A, will be somewhere below the stack. So if I just go 1 byte below that, which is going to be this, still not printed it. Okay, let's just try again. If we go 1 lower, A, print this. Ah, there's my A. Okay, so what does that tell us about the stack? So it says that my A is actually stored in 7FFE, which is it's 2 bytes below 8000, and that just means that when I push the A onto the stack, the highest byte, because I told you that when you push a single byte on, it actually pushes 16 bits on 2 bytes. That's just because the processor is optimized for 16 bits, and you often find when you look into stuff later on, alignment of memory is important for data structures, and so keeping things in line like 16 bits, 32 bits is often important for efficiency. So we pushed ABC on, and we found that the character A was at this address, which is 2 bytes below this. So yeah, that's the reason why. So we pushed on 16 bits, and the lowest byte was the actual character. The highest byte was just 0. So that meant that it was FE, and that means also that if I look at so if I go to C, which is 2 bytes further down below E, there's my B. Okay, so by decreasing the memory, I can see that the stack is growing downwards, which is what I expected. So that's it really. I think that explains the stack. When we in the next lecture we'll look at functions, and it'll be clearer why the stack is useful for that. But basically it's a nice place for us to just store things. We can push things on and pop them off. We don't need to worry about cleaning up the data on there, because when we pop, it just means that that address is available for another push later on. You might think it's restrictive just being able to take things off the top of the stack, but you'll see when we look at functions and when we look at how C compiles into assembly that often the stack is also used to index local data by using offsets in the stack, and there are CPU instructions that are optimized for doing that. But that's enough for now. So we've looked at the stack. Some other interesting things with the stack are that you could, although when you pop things off the stack, they're going to get overwritten when you push something else on the stack. If you've just left a piece of code, somebody else's code, that's pushed things on the stack and that's popped things off the stack and you've not pushed things over them yet, then you can sometimes find other people's data in the stack that they pushed on earlier that's not yet been overwritten. And these things are often used in, like I suppose like exploit techniques, viruses and things like that, or trying to sometimes when a kernel function returns from the operating system, there are some instances where it leaves information on the stack that should only be available in the kernel space. It should be protected, secret information, but they leave it on the stack. So so it's interesting to know how the stack works. Okay, so there we go. Stack. Now let's clean this up because we're going to look at something else now. I'll just get back to my printing a character. Just check my code works. Okay, there it is. So that's my A. Now, if I go back here, now the other thing we're going to look at is control flow. Now we're understanding memory and we're understanding a bit more about how assembly works and the environment that we're loaded into. And now I'm going to look at branching, like how we do if and while loops and stuff like that in assembly. And once we understand that, we can start to, even though it's difficult often to think about things in assembly, like I showed, it's easy to forget what the registers are called, and I've used, I've done quite a bit of assembly stuff. But anyway, it is difficult to work in it. So firstly, you mustn't be too hard on yourself especially while you're learning this stuff. If you struggle and if you get, if the assembly gives you warnings and stuff because you've forgotten to cast a value to a byte or to a word when you're storing it in memory, stuff like that. It's easy to forget that stuff. And that's why we do have high-level languages. It's just not efficient, it's just not realistic to write everything in a low-level language. But to be able to do so is very useful, and to understand how the computer works is useful. So, we'll look at control flow now. And, well, let's see if I can do it without making any mistakes. That'll be good. So I've got my thing here. So I'm gonna try and do an if statement. So I want to be able to say if let's start with some stuff here. Let's put this at the bottom. And I want something like, I want to make something that says like if, let's store a value in dx. So if we move dx 75, I want to say if dx is less than 50, well, let's do something we can put some useful characters on. If it's less than 10, then I want to print a lowercase t, okay. Otherwise, I want to print a capital T. Okay. So how do I do that in assembly? Well, we don't have if statements and we don't have else statements. But all of these in a higher level language are built on two things really. A comparison. So first we do a comparison of of two values to see how they compare, whether one is greater or equal than the other one, whether they're equal, etc. And then we do a jump based on the comparison that just happened. And the jump is conditional, so we jump if something was greater or if something was less or if something was equal. And that's how we do it, so it's a comparison and then a jump. But it means we have to think a bit more carefully about how to do even the simplest of conditions. So I'm going to try and do this one now. So let's have a go. So if I put, so if less than or equal to 10, so first what I have to do is I have to do this instruction, compare. So if I do comp, and I want to say dx, I want to compare dx to 10. Okay, and now alone that won't do anything. What it actually does when I do that comparison is it sets some flags on the result of that thing. It's also the same when you add numbers together in CPU. If I add two 16-bit numbers together and the result would require more than 16 bits, like it would require 17 bits, then it sets an overflow flag on the CPU, and that's how we can chain together calculations to calculate, like to add two 32-bit numbers together. But what it means is that the CPU has some state on the last instruction and it gets stored in the flags register, which is used for all kinds of things. Okay, but we won't worry too much about the flags just yet, but I'm doing this comparison and then I'm going to say jump, and if I look on here, here's just a list of some different jump instructions. So they look like this. There's a few more than this, but these are the basic ones that we can use, and there are aliases that mean the same thing but have different names. But anyway, so we've got these ones which will cover most things for us. So we can say jump if equal, so JE, jump equal. So that means that if we do this comp, if you look up here, so if I say comp xy, and that might be a register or a value, and then I say jump equal, it means jump if they're equal to somewhere, to a target label or an address. And I can say jump if not equal, jump if less, jump if less than equal, jump if greater than, jump if greater than equal. So I use those. So I'm comparing these and I want to say jump, so I want, if dx is less than 10, I want to jump, so let's say jump less, and I'm going to go to a label. Let's make my label. Okay, so less than 10. It's good to use labels that make sense. So I'm going to jump to less than 10. Again, it's usually when you're playing around with these things and compiling it and running it that you really understand how it works. It's not always apparent at first, but you can refer back to these notes and stuff online. So jump to less than 10, and when I want to jump to less than 10, I want to move. It's less than 10, so I'll put a little t, lowercase t, into the AL register, so it's printed. So that's good. If it's not less than 10, then I just this is like my else here, because if I jump when dx is less than 10, it's going to jump to here and it's going to skip this code here. So I can treat this region as the else statement. So I'm just going to put move AL t, so it's a capital T. Right, let's see what happens then, if I've not made a mistake. So I've got, in dx I've put 75, and if I've done this properly, then if dx is less than 10, it should print a little t. If it's greater than 10, it should print a big T. So it should print a big T now. So it printed a little t. So why has it done that? Let's have a look at my code. Okay, so what we see here is if we put, so when I have this in here, so I put 75, and what I'm saying is, so I compare them, and I say if dx is, I compare dx and 10, okay, and I say if I want to jump if dx is less than 10 to this label and print this, which is good, okay. Now, if dx is 75, I'm not going to make that jump, so I'm going to print this thing, okay. But when we look at what happens here, it's printing a little t. It should be a big T because it's greater than 10. So why is that happening? Okay, so what we're finding is this is why we're kind of pampered in a higher level language. But if we look at the flow here, what actually is going to happen is that if this is greater than 75, which it is, so this, it's not going to jump here because it's greater, so it's going to skip this jump and it's going to carry on, and it's going to move capital T into AL, which is good. But then the code is going to carry on executing to this label, and it's going to print, it's going to move the little t, and then so it's always going to print the little t in this case. And just because there's a label here, it doesn't denote it as like a region of code that can't be executed next. The CPU will just go through these. If we looked at the hex bytes, the label doesn't even appear in there. I mean, the label is just a reference for an offset for my convenience when I'm programming. So what happens here is that it will always show a little t. What I have to do is make sure that both of these execute as the next instruction the end of the if statement. So it's convenient often to put something like this. So if I have an end if label, and I don't need to, it just means I don't need to put anything after that. It just denotes the start of the next instruction here. But what it means then is that if I put a unconditional jump, so JMP just means jump in every case, not based on a check. I just put jump to end if, and if I run this, then I get a big T, which is right, because dx is greater than 10. Now if I put something like 9, I should get a little t. Yeah, a little t, that's good. And if I put it on 10, what should I get then? Well, the comparison is jump if less than 10. So it should give me a capital T. Yeah, capital T. So there, the important thing there was that you have to think about where the code's going to execute next. So in this case, I did a comparison. I said jump to this label less than 10, so jump to this offset in the code. If it's less than 10, and execute that, which is good. So if it's less than 10, there's no problems at all. It does that, we get a little t. But if it's not less than 10, we just go straight to the next instruction and remove a capital T in. And it's important now that we jump over this clause, otherwise we end up executing both clauses in the if statement, and we'll always end up with the last one. So I jump over that to my end if there. So there you go. There's how you would write an if statement. So you should be able to build any condition like this. Every sort of, when you have if and then you have lots of Boolean operations, you know, if this and this and this and this, you can break those down into comparisons and then jumps, like I did here, using the different jump instructions for different comparisons. And the unconditional jump, it will just jump directly to that place, which is what we use here. When we put jump $, it just says jump to the current instruction, so endlessly jump and execute the same instruction. Okay, so let's try and do another thing. Let's try and make a loop now. So if I just get my original code back, so it's good to start from a known place. Let's put an X in here. So that should just print an X. Yeah, there's my X. So what I'm going to do now is I'm going to try and print out the alphabet. So to print out the alphabet, rather than printing each doing it manually like 24 times, I'm going to make a loop that just prints through the characters. So I can do that like this. Let's put this down here. Well, first of all, I want to move into AL, the first letter that I'm going to print, so I'm going to print an A. And now what I'm going to do is create a loop. So the way to do a loop is just to jump back to the start of the loop when you get to the end of the loop. That's how you do a loop. But in this case I don't want to jump endlessly and print all the characters out and just carry on printing. I want to just print until I reach a certain character, so I need a condition in there. So I suppose this is a bit like a while loop or a do while loop. This is how we would do it. So let's have a look. So if I've got A in there, okay, so let's put the start of the loop, so let's just call it loop. Now in my loop I want to call this, actually I can keep this outside, because if I don't change that register I don't need to keep setting it. So I've set that up for the bias printing. So all I'm doing is going to change the character inside the AL, the character that will be printed, and then I'm going to print it. So first of all, let's just do this. Let's just build it up. So I've got my loop, and if I want to print this lots of time, well, let's just run it like this. It's always good to build it up. So that prints an A. That's a start. It's good to do it step by step. Now if I want to print more than one A, then I can say jump to loop. Jump to this label. There we go, there's lots and lots of A's there. But I don't want to keep printing A's, I want to print the alphabet. So what I can do then is, well, I want to increment the ASCII value of register AL. So if I start at A and then I add 1 to it, it'll take me to B, the next ASCII character. So if I do add AL, so add just is a way of adding a number to a register. So I'm just going to add 1 to it. That's good. Let's see what happens now. Oh, lots and lots of things. Yeah, that's sort of working, but it's just carrying on printing everything. We want it to stop when we get to Z. So now what I'm going to do is, rather than having a jump loop, I can say I can have a comparison here that says it compares what's in AL. In fact, I can do it. I can do it here. Yeah. It compares what's in AL with the ASCII value of character Z. So remember that when I put this in, when I put quote Z into my assembler, this is just telling the assembler to stick the ASCII character for Z in there, because the computer doesn't know what a Z is really. It's only when it gets printed on the display that the value that I put in there gets interpreted as a Z on my ASCII machine. If I had, I don't know, some other language in there, then it would think it was a different character. So so it's just I'm comparing AL to the ASCII value of Z. And what I want to do is, I've done the comparison, and I want to jump back to the start of the loop if that that value is, let me think. So it's going to be, so I've added 1 to it. So I want to compare, is it Z yet? If it's greater than Z, let's hang on. So we want to jump if it's, every time it's less than equal to Z, we want to jump. That's right. So jump less than equal to loop. So as long as the value in AL is less than equal to the ASCII value Z, I'm going to be jumping, and as soon as it goes beyond that Z, and this jump is not going to happen, so the CPU is just going to continue to the next thing, which is this jump, which is just the end of we're just tagging the CPU then at the end of our code. So let's try this. There we go, the alphabet. So we had a loop there, so we just used a jump like we did before, and we used a comparison to make a loop. So you should be able to, like, taking these instructions here, thinking about those and thinking about using comparisons, you should be able to build up then the equivalent of some statements. So a good way to practice is to start with a simple statement like if if this, do that, else do that, and then do something like if x is less than 10, do this, if x is greater than 100, do this, if x is greater than 1,000, do that, and think about how you can build up your conditions like that. We will look more at this stuff because we're going to be writing some functions soon in the next lecture, so we'll come back to this stuff, but that's I think that's everything really. Yeah, so let's recap. So we looked at the stack, and the idea of the stack was that we could use it conveniently for storing things in memory, temporary things. We could just push them onto the stack and pop them off the stack. The interesting thing about the stack was that it grows downwards in memory, and that we can set the address of the stack, the base pointer, somewhere, wherever we choose, as long as we keep that out of the way of any code or any other data, so that as the stack grows, as we push things onto it, it doesn't overwrite anything else, then we'll be okay. And then we looked at control flow. So we looked at how the way that we implement control flow at the lowest level is just using comparison instructions that compare two values, and then a jump statement based on the outcome of that comparison. And whichever jump statement we use, we'll use, you know, like you can say jump less than. So if the comparison meant that the left hand side was less than the right hand side, then it would jump to the label. If not, it would just carry on to the next instruction. And the thing with those things is that it's very easy to forget to properly complete your branches, so that you don't end up running into the other branch like I did before. So yeah, that's it. So thank you. This stuff will start to make more sense when we start to use it to build up our functions. And once we have functions and we're using logic, we can start to layer up stuff then and forget about it and build on top of it. And that's really how the computer gets, you know, that's how we're able to really use the computer, by layering things up. If one person had to sit down and write the whole operating system and all the software that runs on it, then it would be very, very slow to make the computer do anything. It'd take a long, long time. So we need to abstract things and layer them up. So thank you very much, and I'll talk to you again next time. Thank you.